Welcome back, everyone. Today's explainer takes us straight to the bleeding edge of reality. I know we're all familiar with the basics of quantum physics, but today, we're completely bypassing the dense math. Instead, we're going to distill exactly how these mind-bending concepts actually dictate the universe we live in.
Okay, let's dive into this. What if everything you think you know about reality is just, well, wrong? Now, I know that sounds a bit like science fiction, but seriously, when we zoom in close enough, that solid, predictable world you and I experience every single day, it completely breaks down. The rules that govern everyday macroscopic objects simply do not apply to the basic building blocks of matter.
So here's our roadmap for today. First up, we'll look at the rules of reality. Second, the famous double-slit experiment. Third, we're going to explore the weird quantum world. Fourth, spooky quantum entanglement. And finally, we'll wrap up with why quantum physics actually matters to us. All right, section 1, the rules of reality, classical physics versus quantum physics. And this brilliantly illustrates just how stark the divide really is. On one side, you've got classical physics, right? That's our macroscopic, highly predictable world that follows strict, reliable logic. But on the other side, you've got quantum physics. This is the subatomic realm of atoms and electrons where certainty is entirely replaced by probability. It's a place that completely defies everyday human logic. You know, the doorway into this strange new field was actually kicked open by Albert Einstein. He did this through what's known as the photoelectric effect. Basically, Einstein proved that light isn't just one continuous wave. Instead, it actually carries energy in small, discrete packets that he called quanta. This single discovery shattered the classical rules of the time. It effectively birthed the entire field of quantum mechanics by proving that, on a really tiny scale, energy is delivered in individual, measurable chunks. How crazy is that? Moving on to section 2, the double-slit experiment, the gateway to the subatomic. Now, this experiment is the exact moment where classical logic completely fractures. If you fire electrons through 2 slits, you'd expect to get 2 lines on the back wall, right? But instead, we observe an interference pattern, overlapping waves. But here's the truly crazy part. When scientists place a detector just to measure which slit an electron goes through, that mere act of observation collapses the wave function. Suddenly, they act like solid particles again, giving us those 2 lines. The universe literally changes its behavior just because we are looking at it. It's wild, and it's what we call the infamous measurement problem. So the crucial point here is that this fundamentally proves wave-particle duality. Quantum entities aren't just one or the other. They exist as this bizarre hybrid. They exhibit properties of both particles and waves, and their behavior completely depends on whether or not a conscious measurement is taking place. I know, it's a ton to wrap your head around, but as physicist Brian Cox points out, quote, quantum mechanics and quantum entanglement are becoming very real. We're beginning to be able to access this tremendously complicated configuration space to do useful things, end quote. So this isn't just abstract chalkboard math anymore, guys. This is how the actual fabric of our universe operates. Which brings us to section 3, the weird quantum world, rules of the subatomic realm. To really visualize this, let's borrow a fantastic thought experiment from TED Ed, the quantum foosball game. I want you to imagine you're at an arcade, but instead of playing foosball with a solid little plastic ball, you're playing with a giant, highly unpredictable electron. Sounds chaotic, right? Well, the very first rule you'd run into on this crazy foosball table is the Heisenberg uncertainty principle. Now, in our normal macroscopic world, you can easily look at a foosball and know exactly where it is and how fast it's spinning. No problem. But in quantum foosball, the uncertainty principle dictates that you absolutely cannot simultaneously know exactly where a particle is and how fast it's moving. The more precisely you measure that giant electron's speed, the more its exact location just blurs out and becomes a total mystery. Let's move on and see how this builds perfectly into superposition. Until you look closely, that quantum foosball isn't just in one place. Actually, scratch that. It's more like it exists in a superposition of multiple different states or locations at the exact same time. It is literally everywhere on the table at once until a measurement forces it to pick a spot. It's very much like Schrödinger's famous cat analogy, simultaneously alive and dead until you open the box. And hey, if that wasn't weird enough for you, your quantum foosball can also perform quantum tunneling. This means particles can magically bypass solid physical obstacles, passing right through them as if the barrier wasn't even there. Seriously, no way around it. The particles just gleefully defy everything our human brains tell us should be physically possible. Let's get into section 4, spooky quantum entanglement. connected across space.
Quantum entanglement is, without a doubt, arguably the most terrifying and fascinating concept in all of physics. It happens when two or more particles become fundamentally linked. Once they're entangled, the state of one particle instantly, and I mean perfectly, determines the state of the other, regardless of the physical distance between them. You could put one entangled electron right here on Earth and the other all the way on the other side of the known universe, and interacting with one will instantly affect the other. And there is absolutely no physical link between them whatsoever.
Now, what's really interesting about this concept is that it actually terrified Albert Einstein. He famously called it spooky action at a distance, and he hated it, mainly because it seemingly breaks the ultimate speed limit of the universe, the speed of light. Think about it. If information is traveling instantly across the cosmos, it completely challenges our core foundational understanding of how space and time are actually supposed to work. All right, time for Section 5, Why Quantum Physics Matters, Surfacing Back to Reality.
Now, you might be asking yourself, why does all this abstract subatomic weirdness actually matter to me? Well, by learning to harness these strange laws, we are directly powering the modern world. Quantum mechanics is the engine driving the development of quantum computing, a massive leap that's going to totally redefine human processing power. It enables unhackable, perfectly secure quantum communication networks. It's the fundamental science driving nuclear energy and the future of nuclear fusion. And honestly, perhaps most importantly for your daily life, the physics of quantum mechanics underpins literally all of modern electronics. The microchip inside the very device you're using to view this explainer right now, it relies entirely on controlling the bizarre behavior of electrons.
We've zoomed all the way from familiar macroscopic physics down to entangled particles stretching across the universe and right back out to the tech in your own pocket. So I want to leave you with this final provocative thought. If the very foundation of our universe, the literal building blocks of everything you see, touch, and love, is built on probabilistic, shape-shifting particles that change just because you look at them, what does it all mean for your own reality? Keep exploring, keep asking questions, and I'll see you in the next explainer.